Hello, so here we have the frequency response analyzer. Here is our filter circuit with a 1K ohm resistor and a 1 nanofarad capacitor. The expected corner frequency of this filter is 160 kilohertz. Then here we have our RMS DC converter decoupled with a 10 microfarad capacitor. And then we have an amplifier that amplifies the DC output of the RMS DC converter. And then here's our function generator, and that outputs a sine or triangle wave via the switch over here, and that is outputted through pin 10 here. It goes to the filter circuit. Then here's oscillator. This is 25 megahertz oscillator that runs the digital to analog converter clock on the function generator. And here are the SPI control pins for the function generator. It's used to initialize and reconfigure the function generator to sweep through frequencies and change waveforms. And then here we have a 5.1 volt breakdown zener to prevent overvoltage. And then we have an indicator LED here. So when this button is activated, which is the sweep button, it turns green until the sweep is complete, then it turns back off. The button starts to sweep, which tells the Arduino to sweep the function generator for the filter circuit, and then the DC output goes from the RMS DC converter to the amplifier and then to the Arduino, which is then transmitted over USB to the the frequency response analyzer app, which is made in Python. So let's demo it real quick. Now to begin the demonstration, I'll plug in the Arduino to PC. Computer should beep, notifying the device has been connected, and the green light should turn on the Arduino for power. And should be able to see it on the COM port list. COM 3, Arduino. And then once we're ready, we hit record frequency response. You have 5 seconds to hit the sweep frequency button on the board. Now the green LED is turned on, signaling that it's going through each frequency step. As you can see on the oscilloscope, the frequency is increasing, the wave period is decreasing. And that will continue until it reaches 1 megahertz. There's a time estimation here, so we have 160 seconds left. It should update about, it's every 5 samples, so it's close to 5 seconds. Now that the analysis is complete, the indicator says done, and the LED is turned off. Now we can click display recorded data. And now we can see the frequency response, the magnitude on the y-axis, and the frequency on the x-axis. This is displayed logarithmically. So 10 hertz, 100 hertz, 1 kilohertz, 100 kilohertz, 1 megahertz. So you can see the corner frequency is about here, which is right on about where the expected corner frequency of 160 kilohertz is. You can save the CSV into wherever you'd like, and then you can manipulate the plot by zooming in, so you can zoom in on certain points. So if you want to see here, you can zoom in and you can see the frequency start to rise a little bit here, and then you can pan. You can undo what you just did. And you can save the plot also. So you can save it into a plot here. To demo another filter, here we have an active filter with an op amp. It's powered via a 9-volt battery. And I switched the waveform to triangle. Now I will do the frequency response analysis on this filter. As you can see, the period is decreasing with the triangle waveform. The frequency response analysis is now finished, and now we display our recorded data. We select triangle. And here we can see it's a bandpass filter, which allows a little over 10 kilohertz. This is correct according to my calculations. For the active filter, it's using 1.5 kilo ohm resistor and a 10 nanofarad capacitor, both for the low pass filter and the high pass filter. As we can see here, here are the 1.5K resistors, and then we have 103 capacitors that are 10 nanofarad